So, did you guys have any particular questions about the material I went over on the videos that were posted? Yep.
What exactly do you mean by discriminant?
What? Oh, sure. So your question is, what do we mean by the discriminant? So the discriminant is a particular number that we can calculate if we're given a quadratic polynomial. So like any quadratic polynomial, if you look at it, you can calculate this number called the discriminant, and it will discriminate what kind of solutions you have to the equation. It'll also basically inform you to whether or not it can be factored and how it factors. So in short, I'll eventually open this. So if we have, ax squared plus bx plus c, if this is the quadratic polynomial we're looking at, this is here a, b, and c are constants, right? And what? Also, we assume that a is not equal to 0, right? So that's a quadratic polynomial, and the discriminant is, by definition, it's b squared minus 4 times a times c. So let's just look at 3 examples. If we had, say, x squared plus 6x plus 7, we could look at x squared plus, 4x plus whatever, 13. All right. We could look at x squared plus, well, I keep having pluses. Let me put a minus here. Oh, man. I got to find the juice. I got the juice. I've also got my rag over here somewhere. Wait a minute. Nah, is this the one? See, I've got one for chalk and one for markers. I got to be careful not to mix the two. Now I can tell which one's which. Yeah. No dust cloud. Okay. Okay, so x squared minus 2x plus 1, right? So here you can identify that a, b, and c are what they are, right? So let's see here. This one says a equals 1, b equals 6, c equals 7, right? This one says a equals 1, b equals 4, c equals 13. And this one, if I look at it, I can see, again, a equals 1, b equals minus 2, and c equals 1. These are all kind of boring. A is 1 for each one, right? Because the coefficient of x squared is 1. And then we can calculate the discriminant in each case, right? So b squared minus 4ac for this one is what? 36. So 4 times 7, right? Yeah. So that's 36 minus 28, which is otherwise known as 8, right? This one, so we got 16 minus 4 times 1 times 13, right? That's 16 minus 52, which I think is minus 36. Am I right? I don't know. I think it's minus 36. It's definitely negative, right? The last one here, b squared minus 4ac, what is it equal to? 4 minus 4 times 1 times 1. So the last case, the discriminant is 0, right? So these are the three possible cases for the discriminant. Either it's positive, it's negative, or it's 0. And these will correspond to the nature of the quadratic. Either the quadratic, if it's positive, that means that we can factor it into distinct factors. If the discriminant is negative, that means it's an irreducible quadratic, or sometimes we call it prime. It cannot be factored over the real numbers. If we looked at the graph, it would either open up or down. It would never cross the x-axis. Case 3 is the case that we have a repeated root. Let me go through the algebra since we're here in person. Like the first one, let's talk about, how would we come to terms with it algebraically. What would you do if you wanted to understand what this is? If you wanted to factor this, could you factor this? Right? So this one. So whenever we can factor, we do, right? So this one's x plus 6 times x plus 1. So if I was to look at this, if I was to try to find solutions of the corresponding quadratic equation, what would they be? Did you guys talk about how to graph quadratic equations in intermediate algebra or not? You did? Okay. So there's the factor, right? So what's the, what's the solution of ax squared plus bx plus c equals to 0? What do we have? We have x equals to what? Minus 6 or minus 1, right? For this one. Now this one here, we have negative, right? So if we tried to factor it, we wouldn't be able to do it with real numbers. What we could do here is complete the square and see what happens, right? So basically, when this discriminant's negative, completing the square, well, you can complete the square in every one of the cases. That was one of the things I was trying to get across in the video, is like completing the square is a general operation, algebraic operation we can do on a quadratic. But here, I'll complete the square on this one, just to give you a better sense of what this looks like. So x squared plus 4x plus 13. How do we complete the square here? We do what? X plus 2 squared, right? Because half of 4 is 2. Then what have I done then? I've added 4, right? Because 2 squared is 4. So I have to subtract 4 to be fair. What's 13 minus 4? It's 9, right? So when we complete the square and the discriminant's negative, we're going to end up with a square plus a number, right? So if we set that equal to 0, there are no real solutions, right? There's no way you can have this plus that be equal to 0 just using real numbers, right? So there's no real solutions, but what could we do if we're willing to open our mind a little bit? We could find complex solutions, right? What would the complex solutions look like? Well, once you've completed the square, you can also easily see the complex factoring. See, because once you've completed the square, you could look at that as x plus 2 quantity squared. This 9 is really minus 3 times I squared, since I squared is minus 1, right? Since I squared is minus 1, I can rewrite 9 as minus 1 times, rather minus 9 times I squared, right? Which is minus 3i, which is 3i quantity squared with a minus out front. And so now it's the difference of it's the difference of squares, right? And you can see that the complex factoring here is x plus 2 plus 3i times x plus 2 minus 3i. So I can see from that that the solutions are what? Minus 2 plus or minus 3i, right? Now, what's the other way you could find the complex solutions here? You're like, I don't like completing the square. I didn't understand it in high school, and you're just making it worse. Sorry. I understand. I was that student. I didn't personally properly learn completing the square until I took differential equations, and then it's a force of necessity. You have to do the algebra there for certain things. I understand you can run around it, use the quadratic formula, right? Do everything but completing the square, but I'm trying to tell you, if you take the time to really learn what it's doing, it is very labor-saving. It's essentially doing the quadratic formula in bits and pieces. But the quadratic formula is what? Minus b plus or minus the square root of b squared minus 4ac, right? Divided by 2a. So if we use that for this case, what do we got? B is what? Minus 4 plus or minus square root of what? 16. Well, do I need to do this again? I don't, right? Because what's inside that is the discriminant, which is another good answer to your question, right? Probably the best answer to your question is the discriminant is the part of the quadratic formula that goes inside the square root. But that's minus 36, right? That's all divided by 2. So what we have in this case is minus 4 over 2 plus or minus 1/2. And this is what? Square root of minus 1 times the square root of 36. Right? What's the square root of minus 1? That's what we call I, right? That's the imaginary unit. So we get, and of course this is minus 2 plus or minus 1/2 of I. What's the square root of 36? Well, it's 6, right? And so what do we get? We get minus 2 plus or minus 6 over 2, which is 3i. Which is, of course, exactly what we got with going through the algebra of factoring it over the complex numbers and reading off the roots, right? This half? Oh, sure. So if we have, excuse me, like a plus b over c, then when we simplify, we got to go a over c plus b over c, right? So that too, it doesn't just go with the 4, it also has to go with that, because that's the way we break up a fraction, an addition in the numerator. We keep the denominator for both summands after the. It does seem kind of unfair, right? Like to start with, we've just got 1 2, but somehow after the algebra step, there's 2 2s, right? And I find myself talking about a 2 2 today. It seems wrong, but sorry. Anyway, the last one. What happens? Can you guys see how to factor this one? See, we don't need to complete the square here. I mean, you can complete the square. You take half of this, you square it, then you do what? You've added 1, so you got to subtract 1. But subtracting 1 from 1 leaves you 0. In other words, you've got x minus 1 squared. Completing the square will just reduce to plain old factoring in the case that it's a repeated single factor. So there you go. What are the solutions? Yeah, x equals minus 1. And I usually say twice. It's that's kind of just a point of, now I guess I could probably foolishly try to graph it over here. These will be approximate. But the graph of y equals, so what I'm doing is I'm graphing. Down here I'm going to graph y equals ax squared plus bx plus c. I didn't even talk about that in the videos, right? So I'm adding some value here. So this has x-intercepts of what? Minus 1 and like minus 6, right? And what does it do? It opens which way? Up or down? Well, the coefficient of the leading term is positive, right? So it opens up. It's a parabola. And it's going to look something like this, right? In fact, the y-intercept, we could read off this. The y-intercept is 7. This guy has no x-intercept, so it opens up, right? It never crosses the x-axis. I can read, by the way, once you've completed the square, you can read off the vertex. This reveals that the vertex is at -2, right, for what it's worth. And it also reveals that, in fact, the vertex is at -2, 3. I think. I could be wrong about that. Think for a second. No, the vertex is at 9, isn't it? I think at -2, 9. I mean, if we plug in x equals to -2 into this, we're left with 9. So, but 9 is the smallest that can ever be, if you think about the formula, right? Because you're always adding something positive squared to the 9. So if you think about the values that this expression can take, the smallest it can be is 9. That's where the vertex is in the graph. That's where it opens up from. So that's, crudely speaking, the picture. I could tell you the y-intercept is 13. That's easy to read from the original formula in the so-called standard form of the polynomial. And of course, the x equals -1, that's easy. If it's a double root, that means it bounces off the x-axis like that. And of course, I can also see the y-intercept here is 1. So there's just a crash course in graphing quadratics. I'm sure we'll have lots more problems this semester which come back to graphing quadratics. So this won't be the last time we do this. So I think I answered your question and then replaced it with a host of my own questions and comments. Sorry about that. Yeah.
When you refactor an x squared plus 6x, how do you get factors of x plus 6?
Oh, that's a really good question. The answer is I'm wrong. Now, there's... See, what I wanted here was what? Now, in order to make this modification to a test, you have a lot more math to do. Like, you need to earn like a doctorate in mathematics, or master's would be enough. Once you have earned that, then you're allowed to do things like this, which is what I meant to put there. See, because then the factoring would be like it is. As it is, you're right. That is totally bogus. That is not actually how to factor that. In fact, let me face the music. Well, how does this factor? Curses. X squared. I think it's going to be ugly. So can you factor that nicely? I don't think so. Let me let completing the square show you why. Complete the square here. This is x plus 3 squared, right? If I do that, I've done what? I've added 9, right? So to be fair, I have to subtract 9. 3 squared is 9. So -9 plus 7, that's already there, right? So that is actually x plus 3 squared minus 2, right? And if you tilt your head and squint, you can see that 2 is actually the square root of 2 squared, right? So we can look at this as being the pattern a squared minus b squared, and we know that that is a plus b times a minus b, right? That's the algebra here. Interesting. So, lo and behold, we get x plus 3 plus the square root of 2, x plus 3 minus the square root of 2. So, with this modification, I mean, look here, let me try to say it this way. Let me make if I put this 7 and 6 here, if I change that to 7, if I change that to 6, this is still true. That's true. This is true. This is no longer right. What's the discriminant when we have 7 and we have 6 here? How does that change it? we got 49 minus 4 times 1 times 6, right? 49 minus 24 is 25. So it really doesn't change the the moral of the story here. I mean, it's still positive discriminant evidence. I'm wrong? Yep.
I'm just confused. Why do we switch numbers?
We switched numbers because the factoring that I advertised here was just not true. We would need to have 7 here and 6 there for it to factor with whole numbers, like I did. With the original 6 here and 7 here, it doesn't factor nicely. You need square roots. It's like this. So, the solutions are actually -3 plus or minus 2 with the original polynomial. I made a convenient mistake to factor it nicely, but that was wrong. Right? I mean, if you don't believe me, if you just multiply this out, what do you get? You get x squared plus 6x plus x plus 6, right? Which is x squared plus 7x plus 6, right? That is not what I had here originally. The 6 and the 7 are flipped. Which is why most of you believe me, right? Because you'll just kind of juxtapose a 6 and a 7, just like I did. Of course, I did that on purpose, right? For your learning. Yes. Some of you believe me. Okay. Are we clear on the meaning of the examples, at least now? You know what the discriminant is? Other questions?
On number 3, the solution, should it be, why is it not positive 1?
Oh, have I done that as well? Look at that. So, very good. If this is x minus 1 squared, do we get x equals minus 1 as a solution? No, what do we get? That's right, very good. So, and my graph is what? Yeah, so to fix that, it's pretty easy. We just, well, I guess, fine. I'll do the right thing and just redraw it. So I am so thankful for you guys making corrections to what I'm doing. I'm always interested in these kinds of corrections because I do make mistakes. You know, sometimes to see if you're paying attention, sometimes just because, well, it turns out I'm human. But, yeah. Other questions? Somebody's. What is that? Someone's having a party or something. I used to have one of my classes was in we're in a room next to a German film class, and every so often it gets so loud, the professor would just stop and try to listen to it, you know, because he spoke German. But anyway. It may have been French, I forget. But. All right, let's move on here. We have until when? 1:10, okay. Interesting. Seems like that green marker is bad news. So what I want to talk about now, so I think we're getting a little bit too far behind, and so I think the simple solution, if you guys don't object, is I'm going to omit the section on word problems, if that's okay with you guys. Oh. Surprising. What's that? You're fine with it? So which is so sad because I already picked out like, 6 or 7 of them for you to work. But listen, you'll come back to these in calculus anyway when you study related rates and such. So I'm not particularly concerned about it. You'll come back to it then. And who knows? Maybe we'll find a time to put it back into the course later. But I think at the moment we should go on to inequalities. That's what I'm going to do. So here we go. So how do we solve inequalities? What are the basic, what are the basic rules for inequalities that we have to work with? Let me remind you, here are the rules. First of all, a less than or equal to b implies that a plus c is less than or equal to a plus b. So we can, that was supposed to be plus c. Curses. Ah. Sorry about that. That's supposed to be b plus c. So the point is we can add the same quantity to both sides of an inequality without changing it, right? We could do the same. We could also subtract, right? What if instead of having less than or equal to, we had greater than or equal to? Would these both be true? These would still both be true, right? So you can do the same for greater than or equal to. Now this is will catch people for c greater than 0, and if a is less than or equal to b, then CA is less than or equal to b, CB rather. However, if c is less than 0, then if a is less than or equal to b, then CA is actually greater than or equal to CB. So this is one of the things that will catch people off guard. If we multiply an inequality by a negative number, it switches the inequality, right? Okay, so that's, he has on page 82 of your text, he's got it written out also for the, other, these are also true, these are all still true if we do what? Like make the sensible changes. So for example, for c less than 0, if a is greater than b, then what can we say? CA is less than CB. Okay, so it also works for strict, this is called a strict inequality, right? So strict inequalities do what? They don't include the case of equals, right? So these are the basic tools in our toolkit to solve relatively benign inequalities. Like linear inequalities, we can do direct combat with these and solve them by this method, right? So here's one, like minus 2/3 x plus 8 less than or equal to 3x plus 1. Let's solve this inequality and write our answer in interval notation. So what I would do is I would, first of all, I hate fractions, so I want to get rid of that. Simple way to get rid of the fraction, multiply the whole thing by 3, right? So if we multiply by 3, we have to distribute, right? So this gives us minus 2x plus 24 less than or equal to 9x plus 3. And then what I want to do is I want to put all my x's on one side and all my constants on the other, right? So I'm going to add 2x to both sides, right? And I'm subtract 3 from both sides. So from that I get 21 is less than or equal to 11x. And then I can divide by 11, right? So 21 over 11 is less than or equal to x. This is also known as x is greater than or equal to 21 over 11. For some reason, I prefer to write that. So that's one possible way to write the solution, but I said let's write the solution in interval notation. What's the solution look like in interval notation? x is an element of what? We've got 21 over 11, and it can be as big as it wants, so to infinity. So, this is the solution set to the inequality in interval notation. 21 over 11 to infinity. Okay? Now, so that's great. But if you look at the homework that I'll assign you, this will do about a third of it. Great. I mean, a third of the practice problems I'll assign in this section, this will pretty much tackle. But, nonlinear inequalities, they're going to require kind of a different set of tricks. And let me try to explain to you what I mean by that. So, because there's the nonlinear inequalities, there's something slipperier about them. Let me just get you an example. I really wouldn't advocate doing this example the way I'm about to start to do it. So, if we had x squared, plus 3x plus 2, for example, and I wanted to find where that was, less than 0. How could I do that? Well, if I want to do it just directly, I would factor this, because I can, right? And so that's less than 0. And so what does that imply logically? There are two cases, right? Case 1 would be that x plus 1 is less than 0, and x plus 2 is greater than 0. Case 2 would be that x plus 1 is greater than 0, and x plus 2 is less than 0. Because the only way we can have a product of two quantities be negative is if we're doing what? We're looking at either plus minus or minus plus, right? And then you could solve those separately, right? Like, what would this say? This would say x is less than minus 1 and x is greater than minus 2, right? And what would this one say? X is greater than minus 1 and x is less than minus 2. What does that look like? Can x be greater than minus 1 and also less than, can x be greater than minus 2 but also be less than minus 1? Yeah, it can, right? That's on the number line. If we picture it, it helps. So here's minus 2, here's minus 1, right? So if you think about it, this pair would be satisfied by like an x in here, right? But look at the second case, x greater than minus 1 and x less than minus 2. Is there any x in the real numbers which satisfies that? No, right? So this is basically what you'd say is this is this extraneous case, no solutions here, right? Usually at some point I tell people that if I was to be a rap music artist, that I would go by the tag extraneous G, and then I would my tagline would actually be I'm not even in the solution set. So, this usually works. There was some snickering. Okay, it's good. I do not have any flow. I cannot freestyle. I really have no rapping ability whatsoever. So it's mostly just for the sake of making a joke about the word extraneous, which is kind of a funny word. Anyway, so this is a pain, right? There's a much better way to solve this inequality than using logic. We could use, well, we're still going to be logical, but there's a better technique. And your book uses tables, and that's fine, but I much prefer to use a number line with some pictures, okay? So let me try to walk you through that. I'm going to do the same example, but with the number line. technique. I'll call it number line technique. So what we do is when we're faced with something like x squared plus 3x plus 2 less than 0, because once you understand what I'm about to do, you'll be able to solve pretty much all of the homework in this section. Once you understand this, you can solve nearly all of them. X squared plus 3x plus 2 less than 0, right? So first of all, we make this nicer. This is really x plus 1 times x plus 2 less than 0, right? Fine. Great. So here it is. X plus 1 times x plus 2. I write that over here because that's what I'm looking at, you know? And so there are 2 points of interest, minus 2 and minus 1. Now, this is a polynomial, which means it is a continuous thing. But more to the point, it can only change signs when we cross a 0. When we look at other things, like we'll look at rational expressions where we can basically only change signs either where we're going through 0, we have a hole in the graph, or we have a vertical asymptote. Those are the 3 things we got to watch out for in the expressions that we look at in this section. And so we just put those down on the number line, and we just have to test a point in each case. So like, just plug in, you guys pick any number you like, less than minus 2. May I suggest minus 3? Right? So just think about it. Minus 3 over here, right? Plug minus 3 into this. What do you get? Minus 3 plus 1, which is minus 2. Minus 3 plus 2, which is minus 1. Minus minus is plus, right? So I just go plus, 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 plus like that to indicate that expression's positive over there. Then I pick any point I like between minus 2 and minus 1 to see what happens there. How about minus 1.5? Plug in minus 1.5 into here. See minus 1.5 plus 1 times minus 1.5 plus 2 is what? Minus 0.5 times 0.5, right? Minus 0.25, I guess. The actual number really doesn't matter. What matters is the sign of it. The key here is that that's negative, right? So from that, I write minus, 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 minus. You don't have to write 4. You could write 2, whatever. And then I have to pick some point over here. So I used minus 1.5 as my test point. Over here, I could use, how about 0? 0's there. 0's always nice. Plug in 0 to the expression. What do you get? You get 2, right? So that's what? That's positive. So we go plus, plus, plus. I look at this, and I can tell you immediately the solution is minus 2 to minus 1. Right? And actually, I can easily solve other things while I'm at it, right? If I wanted to solve x squared plus 3x plus 2 greater than 0, what would I do? Or greater than or equal to 0. I look at that number line, and I can immediately write down the solution. That quadratic is non-negative when we're between minus infinity to minus 2 included, and also from minus 1 to infinity included. The reason that there's 2 cases is like if you think about the quadratic graphs I have just erased, unfortunately, you can think about it graphically as well, and it's not surprising that there's 2 regions if you think about it, but more on that when we have more time. So that would be the solution to that inequality. I could just as well solve this example. If I solve that example, it's the same number line because that factors to reveal x plus 1 times x plus 2. It's got vertical asymptotes at minus 1 and minus 2. Again, the same number line. In fact, the solution to that inequality is the same as the first one I worked. Right? So this is what I'm trying to say, is that you can solve a multitude of problems using this number line technique. Now, they have like a table that they use instead, but I think the number line is easier to follow personally. So you can use the method, you can always use the method in the book if you prefer it. but I'll show you what's near and dear to my heart in class. So, all right, so I'll shut up. Sorry, I've gone a minute over. I will try not to do that, but as you know, we kind of started a minute late, so you can hit the stop record. That'd be awesome. It's the big button that you'll figure it out. It's not on the screen. It's actually physically. It's the big on the. See it? Yeah. It's got a red stripe on it. It's okay. Just a second. I'll it's this one.